Hey everyone. I wanted to continue our training. I think I missed last week. Yeah, I was away last week, but I want to continue that today and move on. Last time we talked about functional brain networks, and today cover a topic: can we assess effective connectivity in everyday clinical practice? What are the tools we use to do that? So. That's where we're going to start today. There might need to be a part two next week, but we will begin that. So, can we actually do that in everyday practice is important because if that's what we want and that's what we apply to neurofeedback, that's where we want to look at. So, again, just to review the differences between functional, structural, and effective connectivity. Functional connectivity is basically dealing with correlations, like in pairwise coherence measurements, in fMRI connectivity. That's pretty much the way they do it, although you can do effective connectivity with that technology. Structural connectivity, of course, is the real connectivity that we get from diffusion tensor imaging. And then effective connectivity involves networks and causal effects between neural elements. The idea of being causal is critical here. When we measure something like coherence or phase or asymmetry in most commercial QEEG platforms, these are not causal. These are correlations. And for anyone that remembers their statistics class, correlation does not imply causation. Although when we talk about those metrics, we do imply it. We imply that a coherence measurement means that's the same as connectivity. It's not the same as connectivity. Coherence is a correlation. And when you correlate two regions of the brain, if a third region is correlated with either one of those, it will automatically show a relationship between them all. And these are what we call spurious findings. So it'll show a coherence relationship with that third location paired with one of our original two, but that relationship doesn't actually exist. And it's all because of what happens in the correlational statistic. What we truly need is a causal description, sort of like a regression equation as compared to a correlation, but a multiple regression equation that can tell us what are the causal elements between multiple aspects of brain regions and what's causing what. So that's what we're looking for. It's inferred through statistical techniques such as time series analyses and statistical modeling that assess causality and interaction. So not only can we generate the cause from point A to point B, but we can look at an interaction. So then we can generate a statistic that tells us the cause from point B to point A. So you have it flowing in one direction and flowing back in another direction. In a coherence measurement, there's no directionality. It's only a shared relationship, like a correlation of 0.6. But it doesn't tell us which of those locations is causing the impact on the others or vice versa. In these metrics, we do have that, and we get to something called reciprocal causality, which we'll get to either today or next time. An analysis like this requires complex data processing and modeling techniques such as independent components analysis, which we'll talk about, partial directed coherence, and Granger causality. Granger causality is the metric that gives you these causal elements. Okay, so here's an example of diffusion tensor imaging from a subject on the left that we saw in our clinic many, many years ago. This was a teenage girl, teenage woman with Asperger's disorder. That was a diagnosis back then. And on the right shows a comparison to a normal control. With the highlighted sort of green ball you see in here, it assesses every pathway that flows through that region in terms of diffusion tensors, which is basically the transfer of water molecules or real metrics of structural connectivity. So you can see in the normative example on the right, there's pathways that go all the way up to the prefrontal cortex and then down through the temporal lobes and into the limbic system. This is mainly looking at mirror neuron functioning. So you get full access to frontal lobes, temporal lobes, limbic structures involved in these processes, and this person functions normally because of it. They have normal social skills, interactions, initiation of activity, motivation, drive, etc. On the left, you see that's clearly not what happens with this person. There's no access to the prefrontal cortex, and there's no going down into the temporal or limbic systems, but actually a shooting up to the parietal cortex. Interestingly, what would happen with this person is when they engage with other people, they wouldn't make eye contact and they would start fidgeting and turning in circles and getting very sort of sensory involved. So the picture resembles the symptoms. And a person like this in an EEG should show very clear disconnections between frontal and temporal regions at the very least. This is showing the right hemisphere. This is an example of the same person's coherence measurements in two different metrics. On the bottom, you see pairwise coherences done in the NeuroGuide platform, but it could be any platform because many of the commercial QEEG softwares analyze coherence in a similar way. They measure between pairs and they measure coherence, not causal interactions. And what you'll notice, for those of you who are not familiar with it, any line in blue is significantly low coherence compared to a database. Any line in red is excessively high. And what stands out here is there are no coherence problems shown on the right side from the frontal to temporal regions, either T4 or T6. We'd be looking at probably all of it together. So there should be a band of coherence problems from FP2 to F4, F8, T4, T6, and that's not what shows up there at all. So if you were doing neurofeedback based on that, you would do something entirely different. The software above, which is still coherences, not causal interactions, but now this is a multivariate coherence platform where we incorporate all 19 interactions of sensors simultaneously. And now you see when you have a gap, that's a hypocoherent relationship. Now you can see this gap in the right hemisphere in virtually every frequency from frontal to temporal and even parietal and occipital regions, but especially frontal to all temporal regions. So now it's showing us the relationship we think we should see. So it's better than the pairwise coherence metric. So we've talked before about multivariate compared to pairwise. You definitely want multivariate for sure. This is an example of the same person using a map that incorporates independent components analysis with Granger causality connectivity metrics. And the way you interpret this map is areas in dark blue show low connectivity. So now we're looking at causality, not just coherence or not just a correlation. So you can see right here in blue, all of these connections are very low on the right side from the frontal lobes up through temporal and even limbic regions of the brain. There's two big advantages to this system, even over the multivariate coherences I just showed you. And that is number one, we can source localize every location. So we get the actual precise location in three-dimensional space in brain structure. It could be the cortex, could be the limbic system. It'll tell us exactly where it is. And we get the causal elements, and clearly this resembles what we saw in the diffusion tensor image. There's even areas of red over in here where that activity was shooting up to the parietal lobes. So it actually almost resembles what we saw in the DTI very precisely. So it's very, very interesting information. This is a case of depression. So in major depression, and I think we've talked about this a little bit, but what you see in a PET scan is hypometabolism or underactivity over left frontotemporal limbic regions. That's what we expect in major depression. In a meta-analysis of depression studies with fMRI connectivity, they showed pathways from frontal, orbitofrontal through temporal regions, anterior and posterior, and limbic sites. And again, in fMRI connectivity, these regions show low connectivity all over the left hemisphere, frontotemporal limbic. So we know what to expect in depression. There should be a disconnection, usually a pretty severe one, of left frontal temporal limbic regions of the brain. This is what we see in the coherence metric. Again, the pairwise coherence metric up top. Again, there's nothing showing us a dysfunction across the left frontotemporal regions of the brain. The closest we get is in low beta back to T5 in the temporal lobes and to the middle frontal regions, but not very precisely what we're looking at. In the multivariate coherence map, in comparison, you can see this very severe disconnection in alpha across left frontotemporal regions of the brain. So this is exactly what we're looking for. And it's mind-blowing how different they are, and they use the exact same data file. So this isn't a different artifacting procedure, this isn't anything. We upload the same data here as we do to here, and that's the difference you get. It's staggering. And again, here, you're going to train something very different than you would train down here. Again, here's our ICA and our dipoles showing in the left frontotemporal regions of the brain, areas of concerning activity. And then in our Granger causality, the dark blue regions from frontotemporal limbic regions of the brain, again, localizing those areas in three-dimensional structures and showing us the causal relationship that's low. So here, if we design a neurofeedback protocol, we're going to train across these areas, enhancing multivariate coherence to lessen symptoms of depression. In fact, we've done that, and it shows considerable success. If anyone's interested in me presenting the results of that study, I'd be happy to in a future presentation. So we have a planned break at this point. The next step would be to take you through individual ways of looking at this in individual cases and show you how it applies, and looking at more specifics of the ICA, the Granger causality, the reciprocal causality, all the metrics we glean from this. So I'm going to take a break here and pick up on that the next time we meet. Again, hope everyone has a great Friday and a wonderful weekend and week. Tell your colleagues and friends, invite them to the group, ask questions. If you want to post questions or post discussion elements, I think it'd be great to have more interaction in these groups. And then again, we'll meet again next Friday when I'll do the second part of this. And again, I hope everyone has a wonderful weekend. All right, bye-bye.